G'day guys, in this particular video I'm going to be covering a fairly simple pulleys example problem. Here we've been asked to find the acceleration of block A. This is block A, this is block B, and there's a force P acting on block A to the right. These are the masses of both blocks, and this is the magnitude of the force just here. Now before we begin this problem, I just want to mention that it's implied that we're making certain engineering assumptions, namely that the mass of the pulleys are negligible, the mass of the rope is negligible, and that there's no friction between these blocks and the ground just here. Alright, now that the problem's been stated, have a shot at this yourself first, and then come back when you're done. Alright, well, I reckon the best way to begin solving a problem like this is by making a cut selection around block A so that we can draw the free body diagram of block A. So let's do that. If we were to draw block A just here and its corresponding free body diagram, we would have our force P acting on it to the right, and we'll also have our tension forces from our rope acting on it to the left. So let me draw those. This right here is our rope, here and here, and because we've made cut selections right along here, that means that our tension has now become an external force just here, and of course they will all have the same tension in the rope, and that's because we're assuming that the mass of the rope is negligible and the mass of the pulleys are negligible too. So these tensions are all the same, okay? Now, are we done with our free body diagram? No, we're not. Technically, we also still need to consider the forces in the vertical direction. We've got our force due to gravity, which will in this case will be MAG, and our normal force from the ground acting up on the block, which will be N subscript A, like this. That's our normal force, this is our force due to gravity. Alright, now before I go into trying to analyze all these forces using Newton's laws, let's also draw the free body diagram of this block just here. Now, I'm going to choose this this cut selection just here, like that. Although you can be free, if you wanted to make a cut selection which goes through this blue cable above if you wanted to. You'll get the same result. Now, you'll find that it'll be easier not to make this cut selection, right? Because if you did that, then you'd have a tension force popping out to the right here, and a tension force popping out to the left here, which cancels out. It basically gives you the same thing, but it's simpler just to make this selection just here. Okay, so let's draw that. This is going to be block B just here. And of course we've got our pulley like that. Now we've got our tension forces which are going to be popping out of here too. So this is going to be our tension force T, and this is also going to be our tension force T like this. Now are we done? Technically no, we still need to include our force due to gravity, which will be MBG now. This is a mass MB, and our normal force, which will be N subscript B like this. Now we're almost ready to apply Newton's laws. Let's now define what we mean by positive and negative directions by defining an axis. So I'm going to define, let me continue this wall up here. I'm going to define the position of block A at any time as being a distance XA from this fixed point, from this wall just here. And I'm going to define the position of block B as being a distance XB from the same fixed point. So you can tell that acceleration based off this definition of this axis is going to be positive to the right for both blocks, okay? Now we're ready to start applying Newton's laws. Well, if we apply the sum of forces in the x direction is equal to ma for this upper block, then this is what we're going to get. Well, to the right is considered positive, so we're going to get P minus 3T, right? There's three tension forces, so the combined effect is 3T, is going to be equal to the mass of your block, in this case M subscript A, times by your acceleration of your block, which I will just call A subscript A, like this. Right? Now, unfortunately, we're trying to find A subscript A, but we can't find that because we don't know this tension force. We're stuck, right? This is where this free body diagram comes in handy. If we apply the sum of forces in the x direction is equal to ma for this block, then in this case, we're going to get 2t. 2t is going to be equal to the mass of your block, in this case m subscript b, times by your acceleration of this block, which is going to be a subscript b, okay? So even then, even with these two formulas, we still don't have enough. because we've got three unknowns. We've got t as an unknown, we've got ab, and we've got aa, and we've only got two equations. We need something else. Well, we need a third equation, and we get our third equation by considering this length of rope just here. Let's call the total length of rope L, and let's find out what it is in terms of XA and XB. Well, the length of this part of this rope will be a distance XA, like this. And the length of this part of rope will be a distance XA minus XB. So plus XA minus XB. And the distance of this bit of rope will be a distance XA minus XB as well. And of course, you'll have a whole bunch of extra constant bits of rope here, which are wrapped around the pulley. So of course, you're going to have and constants added to this length of rope. Now, the beautiful thing about this, I know it seems quite disconnected, but the beautiful thing about this is we can differentiate with respect to time, and we can show that 0 is going to be equal to 3 times VA minus 2 VB. Right? And so notice, the length of the rope is always constant, the total length. So that's why this goes to 0 just here. But if we differentiate XA and if we differentiate XB, then we get our velocities of our blocks, VA and VB, like this. And if we differentiate once more, then we're left with 3A subscript A minus 2A subscript B, right? And here we have an acceleration relationship just by considering the length of the rope and differentiating twice. So we have our third equation now, and we can say from this expression just here that the acceleration of B must in fact be equal to, bring it over there, divide by the 2, 3 on 2 A subscript A. So that is our acceleration relationship. Now we're ready to play the algebra game to solve for A subscript A. So let's consider this equation 1, let's consider this equation 2, and let's consider this equation 3. What I'm going to do is I'm going to substitute out this tension force here from equation 2. So we can write this now as equation 1 is going to become P minus 3 times by our tension force, but tension can be given from this, which will be MB on 2 A subscript B, like this. And that's going to be equal to MA A subscript A, like this. Now we can also substitute out AB from this expression and write this as P, let's choose orange, P minus 3 on 2 MB times by AB, which we know is 3 on 2 A subscript A, is going to be equal to A subscript A, like this, right? And of course, now we're ready to just solve this one equation. Let's get AA on the right-hand side. That means we can write AA times by MA plus 9 on 4 MB is going to be equal to P. And then we can solve for AA by dividing by this beast, and then we can say that the acceleration of A must in fact be equal to P divided by MA plus 9 on 4 MB, like this. And now it just becomes a matter of plugging in these values, and if you do that, you will get a value of AA is going to be equal to 2.712 meters per second squared to the right. That is our answer. Alright guys, I hope that made sense. Just as a final summary of what we did, our general process to solve this was 1. Draw the free body diagrams of each of these masses, then define our axes, and then apply Newton's laws, and then get an acceleration relationship by considering the total length of this rope. And then, once you're left with that, solve using algebra to find our values of interest. In this case, it was our acceleration of block A. I hope that made sense, guys, and I hope you learned something. Cheers.